Hello students, welcome back to this series of lecture. In first lecture, we saw the stereochemistry of 1,1-disubstituted cyclohexane. In second lecture, we saw the stereochemistry of cis-1,2-dimethyl cyclohexane. In third lecture, we saw the stereochemistry of trans-1,2-disubstituted cyclohexane. Now, in fourth lecture, we are going to study the stereochemistry of cis-1,2-dimethyl cyclohexane. Let us talk about stereochemistry of 1,3-disubstituted cyclohexane. What is meant by 1,3-disubstituted cyclohexane? The compound in which substituents are present with respect to 1,3 position of cyclohexane. This is carbon number 1, 2, 3. Substituents are present with respect to 1,3 position of cyclohexane called as 1,3-disubstituted cyclohexane. As we know that in case of 1,1-disubstituted cyclohexane, geometrical isomerism is not possible. In case of 1,1-disubstituted cyclohexane, geometrical isomerism is not possible because both substituents are present on the same carbon. But in case of 1,2-disubstituted, 1,3-disubstituted and 1,4-disubstituted cyclohexane, geometrical isomerism is possible, that is cis isomerism and trans isomerism. So 1,1-disubstituted cyclohexane shows geometrical isomerism. One is cis 1,3-dimethyl cyclohexane and second one is trans 1,3-dimethyl cyclohexane. In this series, in this lecture, we are going to study the stereochemistry of cis 1,3-dimethyl cyclohexane. So what is meant by cis isomer? All of you know. Cis isomer means what? Both substituents are present on one side. See, this is moving upward, this is moving upward. Both substituents are on same side. That's why called as cis isomer. Here is also this methyl is moving up, this methyl is moving up. So this is also cis isomer. In case of cis isomer of 1,3-dimethyl cyclohexane, both substituents are either axial or equatorial. So remember, this cis 1,3-dimethyl cyclohexane has two conformational isomer. In one isomer, both substituents are axial, right? That's why cis axial or both methyl group at equatorial. That's why called as cis equatorial form. When these both substituents are axial, on ring flipping, what happen? Ring flipping convert one chair conformation into another chair conformation. Ring flipping convert one chair into the another chair, and during ring flipping, group which is axial become equatorial. See, methyl at C1 carbon is axial, but due to the ring flipping, this axial methyl group is converted into equatorial. Same here, on C3 carbon, methyl is axial, but due to the ring flipping, this axial methyl group is converted into equatorial. Let us talk about its optical activity, optical isomerism. In case of cis-1,2-dimethyl cyclohexane, it is optically inactive. Remember, cis-1,3-dimethyl cyclohexane is optically inactive. Why it is optically inactive? Cis-1,3-dimethyl cyclohexane is optically inactive because of plane of symmetry. Plane of symmetry passing through this C2 and C5 carbon. So this plane of symmetry divides this molecule into two parts. Hence, cis-1,3-dimethyl cyclohexane is optically inactive. So remember, cis 1,3-dimethyl cyclohexane is optically inactive because of plane of symmetry passing through C2C5 carbon. Now let us talk about its relative stability. When both methyl group at axial position, we know that one axial methyl group shows two butane Gauge interaction or 1,3-diaxial interaction. 2 butane Gauge interaction or 1,3-diaxial interaction. Here 2 methyl groups are axial. 2 methyl is axial. That's why this 2 methyl group shows 4 butane Gauge interaction or 1,3-diaxial interaction. As we know that one axial methyl group shows 1,3-diaxial interaction with C3 and C5 carbon. Similarly, 2 methyl group shows 4 1,3-diaxial interaction. That's why the total energy of this axial dimethyl group is 0.9 into 4, that is 3.6 kilocalorie per mole. But we know that in addition to this, here both methyl groups are on same side. So this methyl also shows additional steric interaction, and this additional steric interaction having energy 1.8 kilocalorie per mole. That's why the total energy is how much? 3.6 plus 1.8. So total energy is 5.4 kilocalorie per mole. How? Once again I repeat, one axial methyl group shows 2 1,3-diaxial interaction. Here 2 methyls are axial. That's why 4 1,3-diaxial interaction. One diaxial interaction having energy 0.9 kilocalorie per mole. Here we have 4 interaction. That's why energy is 0.9 into 4, that is 3.6 kilocalorie per mole. In addition to this axial methyl also shows steric interaction having energy 1.8. So total energy is 3.6 plus 1.8 is equal to 5.4 kilocalorie per mole. Let us talk about its diequatorial form. When both methyl group at equatorial, this most stable conformation of cis 1,3 diequatorial 1,3-dimethyl cyclohexane. When both methyl group at equatorial do not shows any interaction, they are far away from each other. That's why energy is 0 kilocalorie per mole. Thank you.